beams and truss structures. So for these reactions for the beams and trusses, you can have applied point loads, distributed loads, and moments, as several examples show. At least this part is for the beams. Right? And this applied point loads, this is beams and trusses. Distributed loads, this part is any variation, right? Evenly distributed, triangular, or something else. If there's something else, you have to remember. Shear moment diagrams. Applied loading. Point loads, distributed, moments. Centroids of areas. trust structures, there's the stability, R plus P and 2N calculations, and then this, for this, Methodist joints and Methodist sections, that's for defined member courses. Right, two different ways, as we've seen. Let's say and zero force members. The understanding of before you do any analysis and how to identify and eliminate zero force members from the problem. It's good to know that, but it also simplifies the problem significantly. It can, not always. Depends on the problem. Moment of inertia for areas, any area, which we're still talking about now, today.
Materials for the exam.
Parallel axis theorem, which we'll be talking about today. And then also the basics of vector analysis, which as soon as we're done with moment of inertia and parallel axis theorem before the end of today, and definitely by tomorrow, we will have covered a certain level of vector analysis. I don't know how much yet. Adding and subtracting, multiplying vectors, and what we get. Okay, so this covers it all. I'm going to take a picture of it myself, since I wrote it here and not here. We have the full class time for the exam. Second homework is due, it's Tuesday, tonight, right? Okay. So I'll make sure the solution set is up and available first thing tomorrow morning, so you have tomorrow to look at. And then the exams the next day. Any questions at all? Comments? Yeah.
For the exam, are you going to like true or false?
No, you were problems.
Problems out, okay, so what is this exactly? Or just say
What is what?
what is this exactly, what the exam will cover? Or-
This is what we've covered in the class up to this, and what you need to be familiar with in order to take the exam. I can't ask everything about what's up here, otherwise the exam, I probably can't. But this is what you're responsible for now. I'm not promising that it will all be on the exam, but there won't be anything beyond this, even if we cover something new tomorrow. Did you, or was it you?
I have a question too.
Yeah, go ahead.
What are we allowed to use on the exam? Can we use like calculators or cheat sheet or anything?
You can use a calculator, not a cheat sheet, but you can use a page of notes. I mean, a single sheet with equations. They just don't call it a cheat sheet. Same thing.
So.
What? And the reason because, so it varies from class to course to course, depending on what I'm teaching, like some of the things. But in this case, there are a lot of different equations. So 1 8.5 by 11 sheet. And I don't want any examples. You have to understand how to apply everything. But you can write equations. I won't provide any equations.
Can we use a graphing calculator?
Yeah, I don't think it's helpful. How would that help? Graphing?
No, just like figuring out the diagrams, I guess.
I mean, you're gonna be, yeah, I know. Yeah, that's fine, if you like it. Any other questions? Oh, yeah.
How big is the piece of paper?
Sorry, what?
How big is
The sheet?
Yeah.
8.5 by 11, regular, sheet this size.
Oh, just one side?
Not like huge. You can use both sides. You can write on the edges too if you want.
Alright.
I'd like to see that. Yeah, you can use both sides. But no examples. I don't want you to have like written out all the example problems and how to do it. Just equations. Any other questions? Yeah.
Are the questions going to be formatted kind of like the homework?
Yeah, they probably would be, but they'll probably be a lot simpler. I mean, there are ways to ask you guys questions. I mean, some of the homework problems might take a long time. And I'll make sure that you have plenty of time. If you know what you're doing, you have plenty of time. You don't feel rushed. If you don't know what you're doing, yeah, it'll feel like you don't have enough time, but that's the way it always is. But if you can do the homeworks and you go through the notes and look at this other stuff that wasn't necessarily on the homeworks, then you should feel ready. I'll give you a bonus problem too. It's an extra 10%. If I forget to put a bonus problem exam, remind me, I'll just write it on. Okay. So yeah.
How many questions?
I have no idea.
No idea.
But it's different because it's summertime. Normally, midterm, the final exam is 2 hours normally in the semester, not in the summer. And then the midterms are shorter because it's the length of the class. You don't have the class for that long, so you have several midterms. In this case, in summer, since we just have 2 exams, a midterm and the final, and because our class time is so long, an hour and 40 minutes that we can be here, so we can use the whole time. And it makes sense because we've covered a lot more material by the time we get to this first midterm than we would at the first midterm in the regular semester. Because I get 3 midterms normally instead of just 1. So anyway, you say you get the whole hour and 40 minutes. How many problems? I don't like to say because let's say I tell you there'll be 6 problems, and then I write the exam. I haven't written it yet, and then I sit down and take it myself before I give it to you guys. And let's say I feel like it's too long for you guys, so then I'll remove one problem, 2 problems, and so then it turns out you get 4, and you're gonna complain even though I did it to your benefit. So I don't like to say ahead of time how many problems. It depends, and maybe one problem have a bunch of little subparts. I don't know. It depends. But the trick is to write an exam where it doesn't take that long to do each problem, but it still gets to all these questions, or some of these questions, not necessarily all of those, for the same reason that I told you. That if I actually ask questions on every little thing here, it'll probably be 4-hour exam. So, but that doesn't mean you're not responsible for knowing this material. This is for the classes. What was the other question?
Is there partial credit? Or is it just
Oh, yeah, it's all partial. Yeah, you can get everything wrong and still get an A. What I mean by that is, like, your final answers can be all wrong, but your logic is right. You make simple little, math errors as you're going down. I don't care too much about that. I'm looking for the process. And so you get a little bit off, but not much, when your final answer is wrong. And of course, it takes longer for me to grade because then I have to follow everything you do. If the answer is right, it's very fast for me to grade. Just look at the answer and take a quick glance at your logic. But if the answer is wrong, and the logic's right, I have to follow you all the way down to make sure you continue that right logic throughout. So that definitely takes quite a bit longer. Yeah.
Does that go the same for the bonus question, or do you have to get that one right?
No, partial credit.
Okay.
I encourage you all to try it, even though it's almost like a trick question often, the bonus. That's the idea. I want you to think, what the old cliche, think outside the box. But try it. Show me a unique way of thinking or trying to solve a problem or whatever. You have to step back and say, okay, it's not the basics that I'm presenting in class. It can be anything. And I've had problems with an object, maybe I will this time, I don't know, it's flying through space and there are various loads applied, or it's sitting on ice, a frictionless surface, and you need to find, let's say, not reactions, but something else, so strange problems. Or it could just be a truss with loads applied in certain ways that the reactions are all exactly zero, but you don't necessarily have to spend a lot of time doing calculations. Maybe you can say, oh, by inspection, blah, blah, blah. Or maybe just a few calculations. Sometimes it's a lot of calculations. It's a bonus. But definitely, if you just give it a good attempt right there, you probably got 2 or 3 out of 10. If you just try it, even if you're way off. And if you have a good idea or an interesting take on it, which is outside of what I've been lecturing on, then maybe you're getting 5, even up to 7 out of 10. It's an extra 10%. The way bonuses work, you can't go above 100 on the exam. So let's say you have a 92 and you get the bonus right, you'll get 100. You don't get 102. 100's the 100. There's no over. But if you have an 80 and you get the bonus right, you get 90. If you have an 80 and you get half the bonus right, you get 85. Is that clear? I should also say about grading in the class, if I either grade in terms of final course grades, straight percentages, or I curve the class. And I do it either way, whichever helps the students more. So if all the grades are really high, then I go straight on percentages because then you get better grades. If nobody here gets above a 90, it doesn't mean no one's going to get an A. I'll curve it. Either way, it's going to help. And the curve is based on the final course grade, not individual things. But I'll tell you the average, and that should give you an idea. The average in this class, let's say on each exam, then I set that to sort of, the average would be set to a middle or high C, okay, in the class, and then it will be spread like a normal curve in either direction, if it's curved. It's not curved when the grades are higher. And it can go either way, for whatever reason. What other questions? So again, this is the material you're responsible for that we've covered or will have covered. All of this by probably the end of this lecture today, and then definitely by the end of this fall. So some of it, probably about half of this, was on the homeworks, or 2/3 of it. Some of it's not, it's in the notes. And I encourage you to look through your example problems and the solution sets to the homework. Your solution sets and mine. And make sure you go through don't just look at the solution set. I would sit down and actually do the problems. And you can look at it if it's different than what you did, and then put the solution set aside and make sure that you can actually do it. Because it's easy to look at my solution set and look at what I did, say, oh yeah, I get it. And then suddenly on the exam, it's like without that solution set there in front of you, it's not so easy. true, false in this exam. So it's all problems, and then you're solving it by hand, writing it out, okay? All right. Let's see if I can make it this time. I made it through the door. I can duck it. There's the centroid of an arbitrary shape. There's a differential area, dx by dy, so it's just a single point, but it has a shape of a rectangle, right? So that we sum up all the little rectangles or squares, that adds up to the total area. I have a line here, which I'm calling AA. I have a line here in the centroid, B prime, AA prime. So from this differential area to here, that's y. And the distance from here to here, from the centroid to that axis AA prime is d. This is the centroid of the area. And we're going to call this distance here y prime. So this is the moment of inertia with respect to that line at the bottom of that area. Y squared dA over the area, this area, and is about that. Now y equals y prime plus d. y prime. So substitute y prime plus d squared for y, dA. So this is just squaring this, and I've separated the three integrals that are there. You have, this is y plus y prime plus d times y prime plus d. So you get y squared, you get a 2d y prime, and you get a d squared. And the d, the 2 and d are constant, so I brought that out of this end. And then, so you have the three different terms, and then you can just separate those. So I can write it here. That's the same thing as that, and then there you can see you just separated them into their three respective intervals. And we pull out the 2d and the d squared. They all have dA. So this first one, this first integral is the moment of inertia about its own centroid. Right, it's y prime starting from the centroid. So moment of inertia of the area about its own centroid. So you can see that here's the centroid, this thing, and it's, let's say it's rotating about that. That's the moment of inertia, not about the base, not about the left. It's about this axis here. It goes right through the centroid. This y prime dA will always equal 0. So that goes out. Called the first moment of the area with respect to its centroid, and which is B, aligned dB prime, and it's 0. So now we have this third one here. This is just d squared multiplied by the whole area. Integral of dA over area is just the area. And so this is what sets up, this is the derivation for the parallel axis theorem, and it's used in various ways. It's used to move the moment of inertia from one location to another. So you have a moment of inertia. Typically, when you have a cross-section, let's say a beam cross-section, you know the moment of inertia always about itself. You don't know what it is about some other location. And that's important when you have a cross-section that's made up not just of one area, but a bunch of different areas. Let's say an I-beam that has two flanges and a web. That's just one example. You can easily calculate the moment of inertia of the whole thing if you have a built-up section made of plates. You get the moment of inertia of the flange, the top plate about itself, about its own neutral axis. You do the same thing about the web, the shear transfer method or member, the web, and then the bottom flange, and then you can add them together by parallel axis theorem. That's just one example. And you'll see example today how we do that. It makes a big difference because the moment of inertia, the flexural behavior and strength of members is basically as composite moment of inertia. Written a little differently. This is the parallel axis theorem. That's the moment of inertia about the centroid, the I bar, and then you have AD squared. A, the area of that part that you're looking at, and then D squared, D is the distance to it, wherever you want the moment of inertia about. I bar is the moment of inertia about the centroidal axis. I, left side of the equation there, is the moment of inertia about any axis. D is the distance between the centroid and the axis where inertia is. Let's look at an example. here in the center. Balancing point. This is x, y, b, b over 2, b over 2, h over 2, h over 2. Y is h. Width there is d, the height of the differential area that I'm showing is dy. So this dA equals b dy. I about x, we'll do this first. That's the moment of inertia of a rectangle about its own centroid, about this x-axis, okay? So here's centroid. So rather than starting at the bottom, I'm starting at the centroid in this integral. Our definition of the moment of inertia about x is the same as y squared dA. dA d dy. Ix is the integral. Y squared d dy. And then the limits, we're starting 0 is in the middle. So y goes from minus h over 2 to plus h over 2 in this case. Okay? So the integral is dy to the third over 3 minus h over 2 to h over 2. Which is b over 3 times the upper limit, h over 2 cubed, minus the lower limit, which is a minus h over 2 cubed. So because this is cubed, that negative stays, right? It still becomes a negative again. Negative, negative, anyway, negative after you cube it, and it's multiplying negative, so this is positive. So it's this plus this term. And again, it's because the limits, we put in the upper limit minus the lower limit here, and that lower limit has a negative. So we end up with hb cubed over 12. Oh, sorry. bh cubed over 12. Yeah. 1/12 base times height. So that's where that expression comes from. For a rectangle, it's always the moment of inertia about its own centroid is always 1/12 width times the height. Total width is the height. 112. So you should commit that to memory, even though you can write it down on the sheet if you want. But just in the future, as a structural engineer, it's always 112 basis. Now I'm doing the same integral, except I'm integrating across in the x direction. My limits will be from minus b over 2 to plus b over 2. So we're going from the descending order. So that's x to the third h over 3 from minus b over 2 to b over 2. Which is h over 3 bracket b over 2 cubed minus b over 2. B squared over 8 plus b squared over 8. It's so it looks the same except the variables change, right? HB, instead of 1/12 base, just a second, instead of 1/12 base times height to the third, it's 1/12 h times base to the third. So it's the same idea, but it's the moment of inertia. So the first one, Ix, is the moment of inertia about, rotating it about this x-axis like this, okay, that way. My y is rotating it this way about this axis in the middle. And so it makes sense by symmetry. The final equation is identical, the variable is just switched. Okay? Because if you made the dimensions b, switch the dimensions h and b, you should get the same moment of inertia either way. Right? Okay, you had a question?
I was gonna say, put squares instead.
Sorry, what?
It should be b half to the third, right? Cubed.
This and that is, and this should be, right? It's correct down. Is that it? That was the corrections. So let's take a break. I'll be back in 10 minutes. About the moment of inertia about its own centroid, so that's just based on its own geometry. And then we just say plus the area times the distance squared between here and here. That's the moment of inertia about some other location. Based on parallel axis theorem, which we derived. And so I have, this is just 1/12 base times height to the third, so base h cubed over 12. That's the moment of inertia about itself, about its own axis, about the x-axis, plus the area, h, right, the whole area. And then d, which is h over 2. So we're just transferring the moment of inertia, bending in this way, instead of about this line, about this line. And then there's the distance, h over 2. Yeah. So don't make it more difficult than it is. The moment of inertia by itself, plus the distance, the area of the whole thing, times the distance squared to any other location, okay? Doesn't have to be at the bottom. You could say, what's the moment of inertia about a line down here? That distance would be from here to here squared. Doing it on the bottom. First started talking about moments of inertia, we started with the rectangle. We integrated it, right? Integral of y squared dA about the bottom. And when we did that, we go back to what we know, dh cubed of 3. Same thing we've done now, using parallel axis theorem, right? Exact same thing without integrating. So we know the moment of inertia about its own centroid, 1/12 base times height to the third. Then we just added the area to the squared. Now we've got transferred the moment of inertia to a different location. Let's make this line B here. And we're going to take the moment of inertia, same rectangle about, so instead of about the, like this, in this direction, about y, we're going to do it about b. We're going to move it over using parallel axis. Okay? So, I, b, equals I, y, plus AB squared. So 1/12, instead of base times height to the third, is base to the third times height, right? The switch, because about the other direction. Plus the area, which is BH. And then the distance, now we're going B over 2. From here. One twelve h d cubed plus h d cubed over 4. before when we used direct integration about that axis. And we used integral x squared dA, and the limits though, instead of minus b over 2 and b over 2, we use 0 to b. Okay? And so instead of integrating, we use a parallel axis theorem for simple shapes, different rectangles, triangles, even parabolic. It's normally rectangle, triangle. This is how you do it. You have a section made of a bunch of pieces, and you can calculate the composite behavior. As you'll see, using parallel axis. You can calculate the moment of inertia about anything. Let's see how we use this parallel axis theorem in a real example as opposed to the variable form. Let's say we have a T girder, the cross section is a T of a beam, so this is the area we're interested in. It's 12 inches, the flange, the top member. 12 inches by 2 inches. Right, that part. And then we have a web that's also 2 inches wide and it's 10 inches tall, like this. And it has its own template. Then we're going to find that there's a centroid, that's open circle, is the centroid of the composite section, right? That we can find, and then we're going to, so we know the moment of inertia, each part about its own centroid, this direction here. And then you got this, but that's not, when it's formed together as a beam, let's say it's welded together here or bolted together with little brackets, they're not going to rotate about their own centroid. You're going to rotate both of them about a common centroid. The moment of inertia we're going to find is about this. This is the composite centroid. And this is Y bar. That's the centroid of the thing acting together. This is the flange centroid here. And this is the web centroid. The web centroid is 10 inches, so this is 5 inches. And the flange centroid is at 11, 10 plus half. So the area is, let's call this 1, and this one 2. So there's only 2 parts, and I'm going to crosshatch it. So this way. So we're going to split areas up there and then this. the beam itself, this is the cross section, so it's not even a straight line across the whole thing. Feels the same, strains and stresses. So neutral axis and the centroid, very important in structural engineering. The area, total area is just 12 times 2 plus 10 times 2. I can't add, that's 40, I said 42 is 44. And, okay, yeah, 24 plus 20 is 42. This was 1. And this is 2. Y bar is the summation of Y bar area over the summation of the areas. Summation of areas is the total area, right? We already calculated. So this is first one, number 1 is Y bar is 11. That's the centroid of its own area. 11 multiplied by the area of 24. Okay. Plus the second one, we go up from here 5. And the area is 10 times 2 is 20. Divide all of that by 44. So this one is from 1. This is from 2. So for this cross section, we get this is 8.27 inches. That's what. So it's, you know, a little less than 2 inches from the top of this web. Not into the image. So again, that's the, if you cut this shape out, both of these shapes and glue them together, so they're one composite section. This is the location where it's balanced. So if you cut it out of cardboard, let's say, and you put it horizontally, you put your finger there, that's the balancing point. And this area, you know, the moments about this line, this area, so this little area is balanced by this line the other way. That's what the center is. Yeah.
We don't need to find X bar, because it's measurable, right?
Yeah, it's right in the horizontal. So we're finding the moment of inertia about this axis. You had a question back there? Someone did? So what I'm interested in is IX, this being X. So it's a moment of inertia about the composite centroid. IX is 1/12 base times height to the third for each of them, plus AD squared for each of them. So we're getting the contribution. They're both being forced to not bend about their own where they would want to, but they're going to bend about this point. That one is, and this one is too. Both of them have this is the D distance for the first one, and this is the D distance for the second one. We're determining the composite moment of inertia, the contribution from each of the elements. And you can have 10 elements in a cross section. In this case, to keep it simple, we just have 2. So we have 1/12 base, that's 12 inches, times height, which is 2 to the third, plus the area, 12 times 2, that's 24. And then the distance, it's 11 minus 8.27 squared. So this is from 1. This is the moment of inertia about itself, plus the AD squared term, right? The distance is 11, that's the distance up, minus 8.27, that's this distance here. This is 11 minus 8.27. Plus 1/12, base times height to the third. You have to know which direction you're talking about. So in this case, So in this case, if the base was this way, 12, height was 2. This is going the same way, but it's oriented in a different direction, right? So in this case, 1/12 base is 2 and the height is 10. 1/12 base, 10 to the third, plus the area of number 2, the second one, that's 20. Multiplied by the distance up, 5, minus 8.27 squared. I would do it as 8.27 minus 5 to keep it positive, but it doesn't matter because you square it. It's always squares. So it doesn't. You can do it in either way. So what we have there is this distance from here to here. Right? And so that's 8.27 minus 5 minus 8.27 is that's D2. The distance from here to here and the distance from here. You can write it. Okay, so this is 2. Rather than just giving you a final number, it's kind of interesting to see the different components. So I'm going to write down all 4 terms. The values, 8 plus 179. That's 167 plus 214. This is from 1, these 2. This is from 2. And then the total, when you add up all 4, is 568. Inches to the 4. 568. This together, this plus this, that's 187. And this plus this is 381. Okay, so 2 things. We notice in this case that the total contribution to the moment of inertia about the composite centroid, in this case was larger from the web than the flange, right? 381 versus 187. But also when we look, we break down the different behaviors. One, the flange had, look how much larger the 80 squared term was. That's the second term. That's where we transfer it rather than the moment of inertia by itself, about somewhere else, okay? So it's much larger because it's oriented in a horizontal direction. The moment of inertia about this way is not that large because the h cubed term is the height, the small value, okay? So the moment of inertia this way, it's small. The big contribution that flange is adding to the flexural moment of inertia or the moment of inertia in the cross section is this A area times the distance here squared. That's much larger. 179 versus 8. You add them together, that's the total contribution of 187 inches to the third, inches to the fourth, for the composite behavior. And now the second one, this web, what you see is similar contribution, 167 and 214. And you break it down. This is the moment of inertia by itself, without, so just the moment of inertia about here, like that. 167 inches to the fourth. And then the area times the distance here squared is 214. So similar. The reason that this 1/12 base times height to the third for the web is so much larger than the flange is because this is oriented, instead of this way, it's oriented this way. So it's bending like this. It's much stiffer in that way. It provides a much more inertia. That's because it's in the equation, it's 1/12 base, yeah, which is smaller, but then the height term is to the third power, and the height is 10. In this case, the height was 2 to the third. That's why. But physically, there's a difference. One's oriented this way, one's oriented that way. So So you get a total of 568. IY, so we know the centroid is, just by inspection, it's halfway across the width because it's symmetry, okay? So this is the composite is here. But notice how it's lined up with the centroid of the two elements. So that means that in this direction, let's put Y here. When we're taking moments about this way, there's no AD squared term in this case, because there's no D. D is 0 for both elements, right? The distance between the centroid of flange 1 and the composite centroid in the horizontal direction and the Y in that direction is 0. So it's just the moment of inertia about itself plus the moment of inertia about itself in that direction. So IY is 1/12, instead of base times height to the third, is base to the third h, or 1/12 h base to the third. It's the same equation, but you just switch what's b and what's h. So it's 1/12 base, in this case it's 2 inch, and then the height term is switched, so it's now in this direction, it's oriented that, so it's the longer direction, 12 cubed. This is from the flange. And then we have the web bending this way, 1/12 base, that's the 10 inches, and then the height in that direction is 2. So it's still 1/12 base and height to the third, and switch what's base and what's h. So 10 times 2, this is from 2. It just says, 80 squared terms are 0 since d equals 0 for both elements. So if it wasn't composite, if these were not connected, this is just a slippery surface, and you apply loads, they would slide longitudinally under bending and shear loads between each other. That means that the moment of inertia of the cross section would not be the same as the composite moment of inertia. It would be the two moments of inertia about their own neutral axes separately, added together. And that could cause complete failure of the structure. If, let's say, you had vertical, if this is, let's say, made of concrete, you had rebar that extends from one to the other. Let's say you didn't put the rebar in, and the two parts were able to slide relative to each other. Now the moment of inertia drops, and it turns out the loads, the stresses that it feels changes, increases, and then the structure doesn't just suffer larger displacements, but larger stresses and failure or early failure. The reason is because the moment of inertia, you no longer would have the composite. So when we look at the first one, remember this part was from the 1/12 baseline section squared. This is from 80 squared. We wouldn't have that 80 squared term. They're allowed to slide. This is why you have connectors between plates. This one is a moment of inertia by itself. You have that, but you wouldn't have that 214. So you would have just 8 plus 167. It's 175. This is for IX. Compared to 568, which is to the fourth for the composite section. So you have 175 over 568 equals 0.13, therefore 31% of composite inertia. So if the bolts, the welding, or depending on the rebar that crosses this plane failed, whatever it is, depending on steel or concrete or aluminum, 2 wood members, if the nails, let's say you nail this together in the wood, and they either aren't put in or they fail, then the moment of inertia of this composite section drops to 31% of what it was as a composite action. And in fact, when you design the number of nails or the number of connectors, whatever, is based on this composite action. So there's a way of determining the longitudinal shear flow here, and then it also tells you how much you have to have crossing over here, and then at what spacing in this direction into the page. So that has enough capacity to force these two, because the reason that there's that shear there is because it's forcing, the fact they're connected is forcing them to act about this point, but it takes a certain amount of load for them. cross-section, made up of, how many elements do you see? 1, 2, 3 rectangles and 2 triangles, so five different pieces, right? Same idea, that's what we just did. We have this one, and I'm gonna put the dots at their own centroids, that's 1. This is 2. 3. And then I have 4. This triangle, and then 5. Right? So we have to include all 5 of those. They're all interconnected, they're all acting together. This distance up to this centroid is 6.5 inches. It's half of 9, which is 4.5 plus 2, that's 6.5. To the first one, it's 11.5, that's this dimension there. So it's 9 plus 2 plus half of 1. It's 11. Let's determine X bar. So that's the distance out to the composite. They need about that. So it's a summation, X bar area over summation area. So 6 multiplied by 12 is 1. That's 1. Number 2. 1 multiplied by 9 times 2 is 18. That's the third one. I go out 3.5. Multiplied by 14. Plus 2, there are 2 of them. 2.67 multiplied by 2. Divided by 48, which is, the area is just 12 plus 18 is 14. So the 2 for the triangle on the far right, that's this 2 times 2, which is 4 divided by 2 triangle, that's the 2. This 2 is there 2 of them, and the centroid for those, let's put, this is 1, 2, 3, and this is 4 and 5. There are 2 of them. So that's the distance out here. We go 2 inches plus, so it's 2 plus 1/3 of this dimension, which is 2 inches. That's right, 2.67 inches. So X bar, that's the distance out horizontally to the centroid, is 3.12 inches. So it's just to the 1 inch to the right of this, it's about here. This is X bar. 3.12. And then vertically, I don't know, let's see, this is 2 inches, I think it's about here. Sections, composite section central. that's a good stopping point. We'll finish this tomorrow and then